Right, so in this video we're going to talk about dark matter. And in order to talk about dark matter, I need to explain some observational kind of things about galaxies very specifically. Now in the previous video we were talking about density of the universe, and the whole point in being able to work out the density of the universe allows us to work out the possible fate of the universe. And obviously go back and watch that video if you're not sure about what I've just said. So dark matter is an unknown mass which is going to explain something very, very strange that we're going to see here in a second. So, for all intents and purposes, what we're looking at here is when we look at a galaxy, so here's a galaxy. So there's my galaxy, and obviously there are stars and there's mass on the different points in this galaxy. And we'll call this point A, we'll call this point B, and we'll call this point C. Now, if we observe the motion of this, okay, if we observe the motion of this, we can kind of do some kind of classical physics on this to work out just how fast these things are moving based on the distance from the center. So in this case, we're this distance, we're this distance, and we're this distance in each case. So we're looking at this from the point of view of, okay, how does the velocity change when I observe and I look at these individual objects? Well, classical physics would tell us that this is circular motion because they're moving in a circle around the galaxy, the center of a supermassive black hole. So we've got mv squared over r, which is equal to the centripetal force, which is caused by this supermassive black hole in the middle. And that is equal to gmm over r squared, which is Newton's law of gravitation. And obviously we can then rearrange that for, we can cancel some m's, and we end up with v squared over r equals gm over r. And we can cancel some r's as well, so we'll just get rid of that r and then obviously the 2. So we end up with v squared equals gm over r, which is a nice equation. And actually from that we can then sub in the replacement of mass, which you will be aware that mass is can be found, so density equals mass over the volume, so mass is equal to density times by volume. So in this case the volume is a sphere because galaxies can be treated as a sphere, so we can say that the mass is equal to the density times 4/3 pi r cubed. Okay, so that's what we're going to sub into this. And you can follow this derivation probably in your book if you're using this equation, and that leads us to finally, when we sub that all in and rearrange it, we get 4 pi g density over 3r. And so what we're looking at here is we're looking at an equation that allows us to work out the velocity at each point r in this galaxy. It's a nice little equation. And so we can plot a graph of it. So what we'd expect from this is because as we get further and further away, the gravitational pull gets less and less. So at the center, obviously we're going to show that the velocity, the rotational velocity, is going to increase up to a point where it starts to lose the gravitational pull, and so as a result, theoretically, we would expect this. We would expect it to drop off as we go with the distance from the center. That's the center of the galaxy. But there's a problem. The problem is this is not what we observe. This is theoretical. What we actually observe is this. Now that's baffling, because that means that the effect of gravity, or the effect of the gravitational pull of the center of this, is not being reduced with respect to r squared. It means that there's some extra mass in this galaxy. And how we explain this, well, we explain this with, you get it, dark matter. Because dark matter means that what we've got here is there is mass that is not just tied up in stars. There's plenty of mass in the star, which means there's there's just as much gravitational pull at the outside as there is in the inside, because most of the stars are considered to be clustered towards the center of a galaxy, which is why we get this effect of the increasing, just like inside a planet, and as we go further and further away, that field effect drops, but that does not happen in the case of a galaxy. So there must be some unknown mass that we have not taken into account. Now, why is this important? Well, it's important because in the context of the previous video where we talked about the critical density of the universe, we have not considered, we were considering all the mass of the universe to be tied up in stars and in planets, etc., etc. But unfortunately, there's more to this than meets the eye. And the current considerations for the universe and what its constituents are made up from, if we were to draw this in a pie chart, we're talking about only 5% is atoms. We're talking about stars, we're talking about planets, we're talking about all that stuff that we see out in the night sky, and us as well. We make up 5%. What about the dark matter then? Dark matter is considered to make up 27%. That is just over a quarter of the universe is made up of dark matter. So what's the rest of this? Well, it's something that we mentioned in a previous video, dark energy. About 68%. So that's quite shocking, I know. And actually, when we look at this, this is a consideration for the density of the universe. Because remember, density is dependent on mass. So it depends on how much mass we have in a certain volume and the volume of the universe. So we've got a certain mass, and that mass we cannot detect, we cannot see, it doesn't absorb, it doesn't emit radiation, which makes this very, very difficult to see, hence the term dark matter. So that's what makes this difficult to observe, but the proof of it is there for everyone to see.